Hi, in this video we will see what is quantum phase estimation algorithm. So quantum phase estimation algorithm is used to estimate the value of phi for this equation, and this equation says that when unitary gate u is applied to its eigenvector phi, then it yields eigenvalue and this eigenvector as it is. So we can compare this example with the examples which we saw in phase kickback video. So here we saw this example when x gate is applied to minus state, then it gives -1 and then minus state as it is. So here this unitary gate is x, and this its eigenvector is this minus state. It gives eigenvalue of -1 and minus state as it is. So this eigenvalue is also represented by lambda, and its value is e power 2 pi I phi. And if we know value of phi, then we can calculate this e power 2 I phi. That's why in quantum phase estimation we try to find the value of phi so that we can find this eigenvalue. Now question arises, why we are doing this, means why it is too difficult to measure this eigenvalue. So let's see some examples. So consider a case when z gate is applied to one state, then it becomes -1. And now when -1 is measured, then this global phase of -1 is just lost, and we just see the 1 in output. So after seeing the measurement, we could not figure out if input was 1 before measurement or it was -1. Similarly, we have these two states, and these two states, if measured, they will either collapse to 0 or they will collapse to 1 with probability of half, or 50-50% chances are there for collapse of 0 and collapse of 1. But if we see here, this one have global phase of 1 upon root 2, this one have global phase of e power pi I by 2 upon root 2. But after measurement, there is no way to distinguish between them. We can't know before measurement if global phase was this or this. So we see the problem here. The problem here is that it is very difficult to detect the global phase by measurement. That's why we need some kind of algorithm, and QPE or quantum phase estimation is that algorithm which help us to measure this eigenvalue by measuring this angle phi. So let's directly jump to the circuit of quantum phase estimation, and for simplicity we just use this simple circuit. The simple example, we will use same circuit. So we will use j gate and we will use state to 1 and see how quantum phase estimation help us to find this global phase of -1. Now how QPE works. So QPE uses two basic principles which we studied in last few videos, phase kickback and quantum Fourier transform. So it uses combination of phase kickback and quantum Fourier transform to calculate the value of phi. Now let's see the circuit, and this is what the circuit of QPE looks like. Here 1 is our state, and G or Z is the gate which we are applying to this state, and we want to measure what is the global state which is applied by this Z to this state 1. So let's go step by step what are steps we take. So in first resistor we pass our input is 1, that's why we are applying NOT gate to the 1. Then we take one more resistor and this one, and we put that resistor in the state of superposition like this. And after that we apply the controlled unitary gate. So we wanted to measure the impact of Z gate on one state, that's why we are applying here Z gate as a control gate, and we apply such that the evaluation resistor is the control and our input one is target. Now why we are doing this, let's try to understand what is the significance of doing all this. So in phase kickback video, if I go back to the top, so in phase kickback video we saw that there are three conditions to have ideal phase kickback effect. First one is that some controlled operations is being performed, and then control qubit should be in state of superposition, and then target qubit must be eigenvector of controlled unitary gate U. And if we see this, then all these three conditions are met here. First condition is that some controlled operation is being performed. So yeah, controlled operation is being performed here. Now control is in superposition. So yeah, control register is in superposition. Also, this J gate and this one state is satisfying this equation, means one is eigenvector of this unitary gate Z, and when Z is applied to 1, it gives eigenvalue of -1 and one state comes out as it is. Since all three conditions are satisfied, phase kickback will happen here, and phase information from target qubit will be transferred to the control qubit. Now control qubit is already in state of superposition, plus it have phase information also, so we can use inverse quantum Fourier transform to extract out the information regarding phase. Now let's see math behind this. So we have input as one state and evaluation register is in state of plus. So at point psi 1 we have plus 1, and plus can be expanded to 1 upon root 2 0 plus 1. After that we can multiply this 1 inside like this. At psi 2 we are applying the control Z gate. So when this control Z gate is applied here, since this is 0 state, control is 0, so nothing will happen here, but here control is 1, so this eigenvalue will be multiplied here. And when Z gate is applied to 1, we know that the eigenvalue is -1 from this relation. When Z gate is applied to 1, we got eigenvalue as -1, so we put value of lambda as -1 here, and then we take out this common 1 here, and now we have 1 upon root 2 0 -1, which is equal to minus state. So at this point at psi 2 we have minus and 1 state. Now we know that for single qubit inverse Fourier transform is just Hadamard gate, so we will apply Hadamard gate, and at this point since here we have minus state, at this point we will receive 1, and that will be our output. Now we will use that output to calculate the phi, but before calculating, let's go to Classiq and execute and see the circuit there also. So this is code for quantum phase estimation in Classiq, and here using OpenQuasm, and I am defining the gate which I want to use, and also here in the params of phase estimation I am defining the size of register which I will use for estimation or evaluation. So let's synthesize the circuit and analyze it. So here we have the circuit. This is our input in plus in one state, and then we apply Hadamard to the evaluation register, and then we apply this control Z, and then we have this Hadamard gate as inverse quantum Fourier transform, and let's execute it and see if the output actually match whatever we saw. So here we got 1 1. This second one we can actually, this second one we need to read, because our evaluation register was Q0, so Q0 is 1 here. This Q1 we can ignore because we just need to care about this Q0. Means if we see the circuit, we just need to care the output of this one. So yeah, we got output as 1. Now let's see how we can use this one to calculate angle phi. So we use this formula. Whatever output we get, we divide it by 2. And for this we do for if we have this single bit evaluation register, we will see how to do if we have more evaluation register, but for single bit we can just divide it by 2, So we got output as 1. So we divide it by 2 and we get 0.5 as phi. Let's put this half in e power 2i phi. So putting half here, it will become e power pi I, and e power pi I is equals -1. And hence we evaluated the value of we evaluated eigenvalue which we get when z is applied to one state. So here in this case we were already aware that value is -1, but if we don't know this value already, then quantum phase estimation can be used to find this value. So now when we verified both mathematically, let's see what's problem here. So the problem here is precision. Right now we are using one bit register, so it offers very low precision. Since we have 1 bit register, output might be either 0 or 1. So when output is 1, phi will become 0.5. When output is 0, phi will become 0. To increase the precision, what we can do, instead of using single bit evaluation register, we can use multi-input, multi-bit or multi-qubit evaluation register like this. And then the way we apply the gates, that will slightly change. So earlier we were applying just a Z gate one time. Now we will do like this. So here I have 3 bit evaluation register. So from first bit I will apply 2 times. From second bit I will apply, from first bit I will apply 1 time. From second bit I will apply 2 times. From third bit I will apply 4 times. And if there is fourth bit, then I will apply 4 to the 8 times, and similarly 16 times, 32 times, 64 times, and so on. So I will just show this circuit in Wikipedia. This is the generic circuit of quantum phase estimation. This is our m bit input state, and this is our evaluation register. So first step is to put all evaluation register in Hadamard or equal superposition. After applying Hadamard gate in all evaluation register, when they are in equal superposition, then from first one we apply controlled gate 1 time. From this one we apply 2 times, then 4 times, 8 times, 16 times, 32 times, and so on. From last one we apply u2 power n minus 1 times, and here we are seeing the powers. So if u power 2 means it is applied 2 times. So instead of showing these 2 boxes, we just write like u square and u cube. That's like. And now how we will measure the output. So let's go to this code again. Now this time I will just keep the code as it is and just increase the bits in evaluation register, and let's see. So this is our input state 1, and these are evaluation registers. First we apply Hadamard gate, then as we discussed we will apply Z gate 1 times, 2 times from second one, and then 4 times from, I just need to keep expanding, but yeah, 4 times from third one. This is our circuit. So hope you got the logic how it works. And in inverse Fourier transform, this is a circuit which we discussed in last video. For now I will just execute it and see the output. So in output we got 100. This one we do not need to take, we just need to take this one. So output is 100. Now, when we have output of quantum phase estimation as 100, we can calculate phi like this. Phi equals 1 upon 2 plus 0 by 4 plus 0 by 8. Here, important thing to note is that right now we have only 3 qubits in evaluation register, this one. Suppose there were more qubits, then we can continue like 0 upon 16, 0 upon 32 and so on. For now, phi will be just equals to 0 0.5. Now, alternative way to solve same thing is that suppose if we got output as 100, then we can convert it to decimal equivalent and divide it by 2 power n, and n will be the number of bits in evaluation register. So we can 100 is equal to 4 and 2 power 3 equals 8. So we can calculate phi like this also, up like 4 upon 8 equals 0 0.5. Now let's see two more examples. So in this one, our unitary gate U is X gate and psi is in state of minus state. Now we know that when X gate is applied to minus state, it gives minus of 1. And just scroll back to phase kickback. So here we saw that when X gate is applied to minus state, it gives eigenvalue of -1 and minus state as it is. So lambda here is -1. Let's run the code in Classiq. So here we are using Quasm, we are defining the X gate here, and first we are applying X gate to our input, then we are applying Hadamard gate, so it will take it to the minus state, and then let's execute it. So here we can see that this is our input register, Q2 is input register which is in minus state, and Q0, Q1, Q3 are evaluation register, and first they are taken in superposition, then X gate is applied 1 times, 2 times and 4 times like we saw for Z gate. I will not expand it here, but same thing is happening here. Important thing here is that while taking measurement, we need to note down Q0, Q1 and Q3. Q2 we do not have to note down. So let's execute it. And in output we see Q0 is 1, Q1 is 0 and Q3 is also 0. So output is 1 0 0. Now if we go here, output is 1 0 0 means same thing will happen. Output is equals to 4 and we will divide it by 8 and 5 will equal to 0 0.5. So for this case, phi is equals to 0 0.5 and lambda means e power 2 pi I5 will be equal to -1. Now let's see for this case where unitary gate is X gate and input qubit is in state of plus. So code will be almost same. This time we will just do not apply this X gate. So we will directly apply Hadamard gate to take to the plus state, and here we have specified the X gate and we will directly run the circuit. So here if you see, this time H gate is applied to 0 state, so it's directly taking to plus state, and these are evaluation register Q0, Q1, Q3 again. Here we are applying X gate similar to last time. I will just execute and see the output. So in output we note Q0, Q1 and Q3 are 0 0 0. So in output we got 0 0 0 and if we calculate phi using it, it will be also 0. So phi angle is also 0 here. Now eigenvalue or lambda will be 1 here because e power 0 is equals 1. And so what it means is that when we apply x get to the plus state, it's like this. Since eigenvalue is not -1, it's just 1 here. That's why we got 1 here. Now let's take another example. This time unitary gate u is this one, which rotates pi by 4 in around g axis, and input qubit is one state. Let's run the circuit and see output. So here we are defining the gate using Quasar, and here we are making from 0 state to 1 state and then doing quantum phase estimation. So this time Q1, Q0, Q1 and Q2 are our evaluation register. Q3 is our input register, which is in state of 1. Then evaluation register is taken to equal superposition, and unitary gates are applied 1 times, 4 times, and 1 times, 2 times, and 4 times. So yeah, rotation is pi by 4. Let's execute it, and after execution we need to measure Q0, Q1 and Q2. So Q0 is 0, Q1 is 0, and Q2 is 1. So our output is 0, 0, 1. We can calculate phi like phi equals 0 upon 2 plus 0 upon 4 plus 1 upon 8. And this time phi is 1 upon 8. And putting this to this equation to the value of lambda, we get e power pi I by 4. So lambda is e power pi I by 4. And what it does mean is that when this gate u is applied to one state, it gives this e power pi I by 4. Let's call it lambda. Lambda multiplied by one state as it is. So that's how we estimated the phase for one state and this unitary gate u. So this was introductory video on quantum phase estimation. Now you can refer quantum phase estimation tutorial of the Classiq, and also you can go through quantum phase estimation notebook for more examples and practice tasks. So yeah, thanks for watching.